Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this news briefing from the ACS Fall 2019 National Meeting in San Diego. We're joined today by Dr. Stephen Zimmerman and Ephraim Morado from the University of Illinois at Urbana-Champaign. They're studying how making polyurethane degradable gives its components a second life. Mr. Morado.
Yeah, thanks for having us here. And it's a pleasure to present our research here at ACS. So we work on stimuli-responsive polyurethanes. And just to give a brief background, polyurethanes are made using two components, polyol monomer and polyisocyanate. And we're able to generate these urethane linkages, making urethane materials that are used for a myriad of applications. One being insulating foams, soft materials such as flexible foams, seen in mattresses, and also elastomeric materials seen on the soles of your shoe. Since a lot of polyurethanes are generated every day worldwide, it's no surprise that they generate a lot of waste, and these polyurethane waste are usually discarded into landfills, and the best way to get rid of them right now is through incineration. So incineration requires a lot of energy, usually temperatures greater than 200 degrees C, and sometimes it could reach to 600 degrees. So we wanted to make a more sustainable polyurethane material. And when people think of sustainable materials, they think of, they think of recyclable materials. However, our approach is a more intermediate approach where we repurpose these materials. We make the starting polyurethane material and then degrade it into a useful starting reagent that we could then react with commercially available and industrially relevant monomers to make a new material. So think about this in a way that we're degrading polyurethane plastics and then turning it into something we could re-commercialize, such as a coating or an adhesive. So our strategy is to degrade polyurethanes at room temperature. As you could see in the previous slides, it takes a lot of energy to actually degrade these urethane materials. So if you go further down. So we have incorporated acid degradable units onto polyurethanes, and it's able to degrade at room temperature, very specifically in 0.1 molar trichloroacetic acid in dichloromethane. And we have established degrading these urethanes at room temperature. And basically, we synthesize these types of elastomeric thermoplastics and turned it into very strong adhesives. So we have degraded those plastics and turned them into really strong adhesives, and also coatings, which is shown right here. And yeah.
Dr. Zimmerman, would you care to add anything to that at this point?
I think Ephraim covered it very well, so yeah,
All right,
I'm here
thank
just
you.
for questions. Yeah.
Thank you. So we are now ready for questions. If you have any, please state your name and affiliation before asking your question. And we will be passing around a microphone. Question at the back there.
Katie Cottingham from the American Chemical Society. So how does the new polyurethane compare to the conventional form with respect to performance and durability and all those sorts of things?
You want to take that, or would you like me to?
Yeah.
Yeah. So we haven't done a really deep dive on the comparisons, so it's been very sort of qualitative at this point. The elastomeric materials are rubbery. We've made some foams as well. They seem to compress and regain their original shape, but we haven't done any direct comparisons to existing materials. But they do seem to be very robust. That's the really critical issue here. If you're building in these breakable units, will it degrade prematurely? And they seem to be really stable.
Laura Cassidy with ACS. Excuse me. So how is the repurposing preferable to recycling? Is it more environmentally friendly, or what's the advantage there?
So I think there's a couple of advantages. One is the process by which we make the original polyurethanes swaps out just one of the two components. So it's a small step from current existing processes where they can continue to use the isocyanates that industry is very comfortable with, and we just swap out the other component, which is called a polyol. So that's one advantage. Ultimately, I think it'd be great to be able to recycle, and there's a lot of really good work that's being done on trying to develop better processes for recycling, but currently it just seems like it takes too much heat, too much energy to break them down. So yeah, our concept was intermediate, just repurpose and reuse.
Question at the back.
Katie Cottingham again from ACS. So have you tested whether this new polyurethane would be safe for people to handle?
I think you can answer that one.
I mean, we haven't tested these polyurethanes if they're safe to handle yet, but these are pretty standard polyurethanes, and I mean, we could basically handle them pretty well after curing. And the toxic part about polyurethane is just the isocyanate of it, and we've done characterizations to assure that all the isocyanates have been reacted.
Okay. And in the press release, it mentioned that you were trying to find a way to make your material dissolve without using water. Why was that important?
So that's a great question. So the unit that we use to cleave the polymer actually would normally cleave with water. The problem is that polyurethane is very hydrophobic. It doesn't like water. And so getting aqueous acid into a polyurethane is nearly impossible. So we built essentially a replacement for water into the polymer chain. So they're hydroxyl groups, alcohol groups that take the place of the water. So it sort of carries its own internal water, if you will.
Okay. And what's your next step for the project?
So the next step would be developing foams that we could repurpose and are comparable, like you said, to commercialized foams.
Yeah, we really haven't looked at the materials properties in great detail, so that's really the next step. And yeah, expanding the number of the types of materials we look at.
Katrina Kramer from Chemistry World. Could you tell me a little bit more about the molecular mechanism of the degradation, and what is the actual unit you put in to make it degrade?
What's the chemistry?
Yes.
Yeah. You want to take that, or you want me to?
I could take it. So we use a acetal unit, and acetal units are known to degrade readily under aqueous acidic conditions. However, as Steve said, polyurethanes are usually very hydrophobic. So we have incorporated an internal hydroxyl group that's able to cleave the acetal backbone and replace the water essentially.
Right, okay. And the breakdown compounds do you reuse? Which part of the breakdown compounds do you reuse for the adhesives you do? Because there's like two starting materials, right, that you put together to make the polyurethane, and then which part do you reuse, basically?
So it's actually it's a new part. So when we cleave, we end up making a cyclic acetal, and that EFRM cleaves to make a new polyol. So then we use that polyol with a new isocyanate to make a new material.
Right. Okay. Thank you.
Sure.
This is Laura Cassidy with ACS again. So your degradation process requires acid and the solvent dichloromethane. Could that create problems for their disposal, or does that have any other, environmental implications?
Yeah, I think the answer is, if you can avoid organic solvents, it's usually best. We have not looked at what the minimum amount of organic solvent is, and I guess you've looked a little bit at which solvents will do it. And so far, methylene chloride looks like it's pretty special.
Yeah.
I mean, it's a very sort of, amazing recipe. It seems very specific to those two components. But I would say we haven't explored it as broadly as we should. Yeah, and there may be ways around the organic solvent. We're thinking about some ways to have it actually degrade in water as well.
Bela Buslig, ACS. Looking at the organic solvents, have you tried some other solvents like DMSO or DMF or anything that would be a little more biocompatible than dichloromethane, for example? And what's the economics of all this? Like, is it really getting to the feasible portion so you can repurpose the thing or reuse it, and so it would make economic sense?
You do the first question, I'll do the second. How's that? So the first question is, what solvents have you looked at?
Yeah, so I did look at DMSO, DMF, ethyl acetate, methanol, and for protic solvents, it doesn't seem to be degrading as well, and also for most polar solvents, it didn't show any degradation, even with added acid.
So second question, is it cost effective?
Yes.
Don't know, because that's sort of, I don't know, it's above my pay grade, I guess. We haven't talked to any companies yet about commercializing it. What I can tell you is the polyol component we've made it on over 50 gram scale, but that's still relatively small. It does involve potassium osmate, which is not necessarily a reagent you'd like to be using. So we're working on ways to have a more sustainable and a more economic starting material for that other component. So this was sort of a proof of principle stage. Yeah,
Thank you.
I would say it's probably not economical at this point.
Any further questions? All right, well, thank you very much. The archived version of this session will soon be posted at bit.ly/ACS 2019 San Diego. Please join us for our next press conference at 1:30 p.m. today on remodeling unhealthful gut microbiomes to fight disease. Thank you very much.